Students, in the last period, we studied the concept of acid and base given by different scientists. Now today, we have to study ionization of acids and bases. Now generally, acid defined as those species which contains H plus ion, and bases are those species which contains OH minus ion. So this is the general definition of acid and base. But here you have to study ionization of acids and base, and therefore you have to remember this ionization of acid and base depends upon the extent of their ionization or extent of their dissociation. So here meaning of dissociation means electrolyte dissolved in water and dissociate into ions, or ionization you can say of acids and bases. So extent of dissociation means if it dissociate completely, then this nature is called as a strong nature, and if it dissociate to less extent, then it is called as its weak nature. And therefore acids and bases on the basis of their extent of dissociation classified into strong acid, weak acid, strong base and weak base. Now first of all you have to study what is the meaning of strong acid. So strong acids are those acids which dissociate completely, in their solution and gives more number of H plus ions. Means once they dissociate completely, then its ionization or dissociation can be shown by only one arrow like that. Means suppose for example if I have to consider HCl is a strong acid. Now in aqueous media it dissociates into ions, and it will dissociate into ions as H plus ions and Cl minus ions. So H plus aqueous, Cl minus aqueous. So this is called ionization of strong acid, and it can be shown by single arrow. Suppose another example, that is the strong base. Now what is the meaning of strong base? Similarly, once you know the strong acid that contains more number of H plus ion, similarly for the strong base that contains more number of OH minus ion. Means strong base are those bases which dissociate completely in their solution and gives more number of OH minus ions. Means dissociate to large extent, means you can say practically completely, and gives more number of OH minus ions. And therefore if you have to consider example NaOH in their aqueous media, it will dissociate as Na plus aqueous plus OH minus aqueous, and hence its ionization can be shown like that by single arrow. So this is called as a ionization of strong acid and strong base. So all of you remember, students, so if the acid is strong or base is strong, and if you have to write the ionization or its dissociation, then it can be shown by single arrow. Suppose for another example of strong acid, HCl number 1, then HNO3 is also strong acid, then HClO4, it is also strong acid. So in this way you have to remember these are the strong acid. HBr is strong acid, HI is a strong acid. So in this way you have to remember these are the strong acid, and if you have to show the dissociation of these acids, it can be shown by single arrow. Similarly for the strong base, you can say like that NaOH is the best example of strong base, KOH is the best example of strong base. So in this way you have to remember first these ionization of strong acid and strong base. Now another way you have to remember ionization of weak acid and weak base. So its ionization is also depends upon the extent of dissociation. So what is the meaning of weak acid? So weak acids are those acids which dissociate to very small extent. Dissociate to very small extent and gives less number of H plus ions in their solution. Means dissociate to small extent, and once it dissociate to small extent, then it gives very less number of H plus ions, and therefore such acids are called as a weak acid. Suppose for example, if you have to consider, there are so many examples. Acetic acid is a weak acid. In their solution, means in aqueous media, it will dissociate as CH3COO minus aqueous plus, that is the H plus aqueous. But this dissociation can be shown by double arrow. Why it can be shown by double arrow? Because this solution contains partially acetate ions, partially H plus ions, as well as undissociated CH3COH molecule, and therefore its dissociation can be shown by two arrows: reactant to product, product to reactant. So in this way you have to remember dissociation or ionization of weak acid. Similarly, you have to remember that is the ionization of weak base. So what is the meaning of weak base? So weak base are those base which dissociate to very small extent, and it gives less number of OH minus ions in their solution. Means less number of OH minus ions in this solution, then definitely it is called as a weak base. Suppose for example NH4OH, ammonium hydroxide, is a weak base. In their aqueous solution, definitely it will dissociate as NH4 plus ions plus OH minus ions. But this solution contains partly NH4 plus ion, partly OH minus ions, and unionized molecule, and therefore equilibrium will be exist like that, and hence it can be shown like that. And this is nothing but called as a dissociation or ionization of weak base. So in this way you have to remember what is the meaning of ionization of acids and bases. There are so many examples of weak acid. You can say formic acid HCOOH, you can say hydrocyanic acid HCN, you can say carbonic acid H2CO3, you can say formic acid SCOH. These are the weak acids, and while writing the ionization of that weak acid, you can show by here two arrows. Similarly, weak base, there are so many weak bases. So FeOH thrice, ferric hydroxide is a weak base. CuOH twice, that is the copper hydroxide, is a weak base. Pyridine is also weak base. So in this way you have to remember that is the ionization of weak acid and weak base, as well as ionization of strong acid and strong base. Means in short, you have to complete this bit, that is the ionization of acids and bases. Now once you know the ionization of acids and bases, then related to that you have to study dissociation constant or ionization constant of acids and bases. Dissociation constant or ionization constant of acids and bases. Now you have to know the ionization of acid and base. Now you have to study dissociation constant. Now here dissociation constant for acid. Dissociation constant for acid. Now suppose for example, general example I can say HA is a weak acid. Generally dissociation constant you can write for weak acid or weak base. So suppose here HA is the weak acid, it will dissociate as H plus ions as well as A minus ions. You can say acetic acid, you can say formic acid, you can say carbonic acid, you can say benzoic acid, like that. So many examples you can take here. So HA, it will dissociate like that, H plus plus A minus ions. So when law of mass action is applied, in the 11th standard you know what is the meaning of law of mass action. So when law of mass action is applied on this equation, then you have to take the constant that is called as a K. So K is equal to concentration of H plus ion into concentration of A minus ions divided by concentration of HA So here this K is nothing but it is called dissociation constant. Now this K is for acid because H is taken as an example for acid, and therefore instead of K only you can write as a Ka. So K for dissociation constant and A stands for acid, and this Ka is nothing but it is called dissociation constant for acid. Suppose for example if you have to consider acetic acid, you have to write the dissociation constant for that acetic acid. So CS3COH in aqueous media, it will dissociate partially as CS3CO minus ions in aqueous media plus H plus ions in aqueous media. Applying the law of mass action, then you can write the equation directly. I can write here Ka because acetic acid is the acid. So Ka is equal to concentration of ions CS3CO minus ions into concentration of H plus ions divided by concentration of CS3COOH. So this Ka is nothing but it is called dissociation constant for acid, and which acid? That is the acetic acid. So in this way you have to remember that is the dissociation constant for weak acids, and generally dissociation constant values for the weak acid is always less than 1, and for the strong acid it is always greater than 1. So you have to remember this additional point. Now once you know the dissociation constant for weak acid, similarly you have to remember dissociation constant for weak base. Now generally weak base I consider it is the BOH because those contains OH minus ions in their solution called as base. Therefore I consider the BOH is a weak base, and once it is weak base then feebly or partially it is dissociated as B plus ions plus OH minus ions in their solution. Now applying the law of mass action on this equation, when law of mass action is applied on this equation, then this equation is called, then this equation can be written K is equal to, so this K is nothing but called as a dissociation constant for base. So BOH is a base and therefore I can write Kb. So Kb is equal to concentration of B plus into concentration of OH minus ions divided by concentration of BOH aqueous, and this is nothing but called as a dissociation constant for base. Suppose for example actually you have to consider NH4OH is a weak base, then how you can write the dissociation constant? So NH4OH aqueous dissociated partly as a NH4 plus ions plus OH minus ions. Applying law of mass action, then it will be obtained, that is the constant called as a dissociation constant. So dissociation constant for NH4OH, that is the Kb, is equal to concentration of NH4 plus ions plus into concentration of OH minus ions in aqueous media divided by concentration of NH4OH. So in this way you have to remember this is nothing but called as a dissociation constant of weak base. So in this way you have to remember what is the meaning of dissociation constant. Now student, once you know in detail about the dissociation constant for acid as well as base, then how you define dissociation constant. So dissociation constant for weak acid, weak base or electrolyte, you can say dissociation constant for weak acid, suppose for example, then always it is written as K. Dissociation constant for weak base, always you can write Kb, or dissociation constant for weak electrolyte, then you can write as a K. So this is the notation regarding with dissociation constant. But how you define dissociation constant? So dissociation constant is nothing but it is always equilibrium constant. And this equilibrium constant can be obtained by applying law of mass action on dissociation reaction of weak acid or weak base. So this is the general definition. So it is the equilibrium constant can be applied to the dissociation equilibrium reaction. In another way also you can say it is the equilibrium constant, and this equilibrium constant can be obtained for which reaction? That is the dissociation reaction. And that dissociation reaction means at which state? At equilibrium state for weak acid or weak base. So in this way you have to remember what is the meaning of dissociation constant for weak acid as well as weak base. So same point you have to remember, dissociation constant values for the weak base is always less than 1 in the range generally 10 to the power of minus 4 to 10 to the power of minus 10, and dissociation constant values for the strong base is always greater than 1. So in this way you have to remember what is the meaning of dissociation constant for weak acid as well as weak base. And once you know the dissociation constant, then you have to study one important law that was given by the scientist Ostwald, called as Ostwald dilution law in the year 1888. Ostwald, name of the scientist, he gave a quantitative application of Arrhenius concept of acid and base. Arrhenius concept of acid and base. So this law related with quantitative application. And कोणाच्या संदर्भात quantitative application given by Arrhenius concept of acid and base. Second point you have to remember, this law related with degree of dissociation and concentration of solution, or also dilution or volume of solution. So second point you have to remember, Ostwald dilution law is related with degree of dissociation. You know in the last period what is the meaning of degree of dissociation. Mathematically it is represented as alpha, and concentration, that is the C, or alpha, and that is the dilution of volume, that is the V of the solution. Third point you have to remember, this law is applicable only for weak electrolyte, and only for weak electrolyte means maybe weak acid or maybe weak base. So in this way, first you have to remember general information about the Ostwald dilution law. So Ostwald dilution law is quantitative application of Arrhenius concept for acid and base. Ostwald dilution law shows the relation between degree of dissociation and concentration of solution or volume of solution. And third, Ostwald dilution law is applicable only for weak acid or weak base. Means in short or general point you can say weak electrolyte. So you have to study the Ostwald dilution law, or you have to study mathematically what is the equation for Ostwald dilution law for the weak acid. So here Ostwald dilution law for weak acid, and very easy equation that was given by the Ostwald. Now generally you have to consider that is the HA is the weak acid because it contains H plus ion when dissolved in solution or dissolved in aqueous medium. So HA partly dissociated as H plus ions plus A minus ions. Now applying the law of mass action, law of mass action, this equation becomes Ka is equal to, directly I write Ka, because you know applying the law of mass action always you get constant, and this constant is nothing but called as a dissociation constant. This applied for the dissociation equilibrium of weak acid, and therefore dissociation constant of weak acid. So Ka is equal to concentration of H plus ion into concentration of A minus ions divided by concentration of Ha. Okay. Now important point you have to remember. Now here you have to consider Ha is the weak acid. But how much quantity you have to consider? So always you have to consider 1 mole of Ha weak acid. Okay. Now present in how much volume? Because Ha in aqueous medium. So how much aqueous quantity is to be taken? So for that always you have to consider 1 mole of that weak acid present in phi dm cube of solution. Phi dm cube of solution. And once the weak acid present in whatever may be the dm cube of solution, then always it feebly dissociated or feebly ionized into ions. And once it dissociated, then this degree of dissociation is nothing but it is called alpha. So alpha is nothing but it is the degree of dissociation. Now to remember, 1 mole of Ha weak acid present in phi dm cube of solution, and alpha is the degree of dissociation. And now this reaction present at equilibrium. Then what about this Ostwald dilution now? So you have to remember Ha aqueous medium feebly dissociated as H plus aqueous plus A minus aqueous. Now you have to consider initial mole of Ha, initial mole of Ha, that is the 1 mole H plus ions plus A minus ions. So what is the initial mole of H plus ion? So here 0. Why it is the 0? Because initially 1 mole of Ha is present. Reaction is not start, and therefore the initial mole of H plus ion is 0, and initial mole of A minus ion is also 0. Now reaction is start. Now Ha dissociated feebly or partially into H plus and A minus ion. Again H plus A minus ion combines to give an ionized Ha molecule, and in this way equilibrium is present. So at equilibrium the number of moles at equilibrium. So what is the dissociation? Alpha. What is the initial mole? 1. And therefore number of moles at equilibrium will be 1 minus alpha. Because initially 1 mole, degree of dissociation is alpha. Therefore at equilibrium its mole of Ha becomes 1 minus alpha. So what is the initial mole of H plus, number of moles at equilibrium? That is the alpha. What is the number of moles of A minus? That is the alpha. Because initially reaction is not started, then initial mole are 0. Now reaction is started, and at equilibrium it dissociated is alpha. A minus is also dissociated as alpha, and therefore number of moles at equilibrium for Ha 1 minus alpha, H plus that is the alpha, A minus is also alpha. So what is the equilibrium concentration in moles per dm cube? Moles per dm cube. Now generally what is the concentration? Number of moles divided by volume. Now what are the number of moles at equilibrium for Ha? These number of moles are 1 minus alpha. And how much volume you have to consider? Phi. And therefore 1 minus alpha by phi is called as equilibrium concentration. Only concentration 1 by V. 1 mole dissolved in dm cube of solution. But here you have to consider equilibrium concentration, and therefore equilibrium concentration is 1 minus alpha by phi. What is the equilibrium concentration of H plus? Alpha by phi. What is the equilibrium concentration of A minus? That is the alpha by phi. So in this way, you have to remember that is the when HA, weak acid, dissociated in their solution, dissociate into H plus and A minus ion, and you will get data like that. Now applying law of mass action, you know that Ka is equal to concentration of H plus into concentration of A minus ions aqueous divided by concentration of HA aqueous. Now these square brackets here represent as equilibrium concentration. So all of you know what is the equilibrium concentration of H plus? Alpha by V. What is the equilibrium concentration of A minus ions? Alpha by V. What is the equilibrium concentration of HA? That is the 1 minus alpha by phi. And therefore you can put this value, you can write alpha by phi into alpha by V divided by 1 minus alpha by phi. Now solving this equation becomes Ka is equal to alpha square upon V square, alpha into alpha, alpha square into V square into phi divided by 1 minus alpha. So in this way you have to remember this alpha square upon V square up into V upon 1 minus alpha. So this 1V, this V will be cancelled and it becomes alpha square upon 1 minus alpha into phi. So this is the first form of Ostwald dilution law for the weak acid. So all of you remember that, which is the first form of Ostwald dilution law. So Ostwald dilution law can be written as a for acid Ka is equal to alpha square upon 1 minus alpha into phi. So in this way you have to remember this is the first form of Ostwald dilution law for weak acid. But you know that phi is equal to 1 by C because C is nothing but it is the 1 by V, number of moles divided by volume. Therefore V is equal to 1 by C. You have to substitute this value in this equation. Then this equation becomes Ka is equal to alpha square upon 1 minus alpha into 1 by C, means this C will be go in that side and it becomes alpha square C upon 1 minus alpha. So this is the second formula of Ostwald dilution law. Now you know that alpha is degree of dissociation. Degree of dissociation is always fraction. It's very small, and therefore if you have to subtract from this 1, the remaining answer will be nearly equals to 1, and hence the alpha, that 1 minus alpha you can say, is nearly equals to 1, because this alpha for weak acid, the value of alpha for weak acid is very small, and hence you can write Ka is equal to alpha square C. So this is the third formula of Ostwald dilution law for the weak acid. So first formula, K is equal to alpha square upon 1 minus alpha into V. Second formula, K is equal to alpha square C upon 1 minus alpha. And third one is Ka is equal to alpha square C. But suppose we have to ask, what is the statement of Ostwald dilution law? So basically I say, this Ostwald dilution law shows the relation between degree of dissociation and solution of their solution. And therefore I write here, alpha square is equal to, this becomes Ka upon C. And hence you can say alpha is equal to square root of Ka upon C. So this is the relation. From this relation you can say that degree of dissociation of a weak electrolyte is always inversely proportional to square root of its concentration of a solution. And instead of concentration, if you have to put the volume, then alpha is equal to, because C is equal to 1 by V. And if you have to put this value, then this equation becomes alpha is equal to Ka into V. Because C is equal to 1 by V, मग ते V वरच्या बाजूला गेला, alpha is equal to K into phi. Means in another way you have to say the degree of dissociation of a weak acid, means weak electrolyte, is directly proportional to the square root of dilution or square root of volume of a solution. So in this way, you have to remember Ostwald dilution law for weak acid. So final statement. So Ostwald dilution law can be stated as degree of dissociation of a weak electrolyte, means weak acid or weak base, is inversely proportional to square root of its concentration or directly proportional to square root of its volume or square root of its dilution of a solution. So in this way, you have to remember that is the Ostwald dilution law for weak acid. And once you know systematically this Ostwald dilution law for weak acid, then it is very easy. Same way, you can write the Ostwald dilution law for weak base. Now, how you can derive Ostwald dilution law for weak base? Same way you can derive. Now, which is the general example for weak base? That is the BOH. So, BOH in aqueous media dissociate feebly or partially as B plus ions plus OH minus ions. Then here BOH is considered as a 1 mole of that weak base BOH that is dissolved in pdm cube of solution, and alpha is degree of dissociation. Degree of dissociation. This is the same way. So 1 mole of BOH electrolyte or BOH weak base dissolved in aqueous media, then it will dissociate as B plus and OH minus ions partially. And 1 mole of BOH dissociated, then its data will be like that. Reaction, you can write again BOH aqueous, it will use as B plus aqueous plus OH minus aqueous. So what is the initial mole of BOH? Same you can write. Initial mole of BOH is 1. Reaction is not started, therefore initial mole of B plus and OH minus ions are 0. Then number of moles at equilibrium, that is 1 minus alpha. Same way, here alpha, and now equilibrium concentration in moles per dm cube, that is 1 minus alpha by P and alpha by P. So once you have to know all these terms, then you have to put this value by applying law of mass action on this equation. Now applying law of mass action on this equation, then equation becomes Kb is equal to concentration of B plus into concentration of OH minus aqueous divided by concentration of BOH aqueous. Now you know the equilibrium concentration of B plus alpha by V, OH minus alpha by V, and BOH is 1 minus alpha by V. And substituting this value, we will get the final equation for Ostwald dilution law. So here Kb is equal to what is the equilibrium concentration of B plus alpha by V, OH minus alpha by V, and for BOH 1 minus alpha by V. Now once you know this equilibrium concentration, you have to put this equilibrium concentration in this equation, that this equation becomes like that. So alpha into alpha, alpha square upon V square into V upon 1 minus alpha. So this V and 1 square V will be cancelled. So it becomes Kb is equal to alpha square upon 1 minus alpha into V. So this is the first form of Ostwald dilution law. But phi is equal to 1 by C. So substituting this value, you can write Kb is equal to alpha square upon 1 minus alpha. Phi is equal to 1 by C, and therefore you can write like that. Kb is equal to alpha square C upon 1 minus alpha. But for weak base, means weak electrolyte, 1 minus alpha is very small, means alpha is very small. Therefore 1 minus alpha value nearly equals to 1, and hence you can write Kb is equal to alpha square C. So this is the third formula of that is the Ostwald dilution law, and hence again it shows the same relation, and same relation is alpha square is equal to Kb upon C, means alpha is equal to square root of Kb upon C, or alpha is equal to C is equal to 1 by V. Hence you can write alpha is equal to Kb into V, and this is nothing but called as a Ostwald dilution law for the weak base. Means it shows the relation between degree of dissociation and concentration as well as dilution or volume of the solution. So again, what is the statement of Ostwald dilution law? Degree of dissociation of a weak base is inversely proportional to square root of its concentration, or directly proportional to square root of its volume of a solution. So in this way you have to remember that is the Ostwald dilution law for weak acid as well as weak base, and with that here you have to complete that is the Ostwald dilution law.